Right, so my name is Eduardo. I wanted to start with a story today. So I'm driving my car in France somewhere, and close to the border with Belgium. And it's a horrible day, really a horrible day. It's raining. That will make today look like it's a summer day in Brazil. So it's horrible, it's cold, it's dark, it's the end of the day. And I'm very tired. And I kept postponing refilling my tank. Let me put it this way. And then I get the sign at the panel that says, you have 25 miles to go. And then at some point, I do have to refill my car, otherwise I'm in trouble. When I see that, I'm like, okay, I cannot postpone that for much longer. I see a traffic board that says a fuel station in 20 miles. And that made me very happy, because I thought, I have 5 miles to spare. So that was good. So I continue. I think, okay, this is going to be fine. But then somehow the car wasn't being totally honest with me, because it turns out that when I see another traffic sign that says a fuel station in 15 miles, my car also says, you have 15 miles to go. And then I start to get nervous, because I'm thinking, I may not make it. So I continue driving, and I start to get pissed off, because the car keeps lying to me. And it turns out that in 5 or 6 miles to go, or 5 or 6 miles to get to said fuel station, suddenly it just says, out of fuel. And it feels very humiliating, because even though it says you don't have any fuel, so it blinks in your display and it makes a noise, so it's like the car telling you, you're an idiot, you should have refilled 4 hours ago. You can still go for some time. So it's not like you are automatically out of fuel. So is that expectation, will I make it or not? And to cut that long story short, well, it turns out I do not make it. Just shy, 1 mile. And then I said, okay, well, I have to go out. And like I said, it's this horrible day, a lot of rain. And then I find a 600 ml bottle in my car. So I carried that to the fuel station. I put 600 mils of fuel. And then I walk back holding that bottle, as that's the most precious thing I ever had. And, and then everything is fine after that, but it's just not a great feeling. And after that day, I really started to wonder about systems, or these numbers that would come out of systems in ideal case scenarios. And that's, I think, a good motivation to why we are doing this work in anomaly detection using a vocabulary-free algorithm. So my name is Eduardo. I'm head of security analytics for ING, for the cybersecurity office, and I'm a visiting researcher in the cybersecurity lab at TU Delft. I want to acknowledge my contributors, Daan, who wrote a master thesis out of that, so I will share the link with you later. Yury and Anna, 2 assistant professors at TU Delft, who are also part of that research. So let me give you the takeaways that I want you to remember after this presentation. So you need to evaluate your stuff against real-world data. Not to go back to that point where, your car says you have 25 miles and turns out you have 14. The algorithm that we are going to show here also enables learning from sequential data, and I'll go a little bit more in detail later on. We also made the algorithm more robust, so it works for this unstable log data, and that comes in a second as well. And in terms of explainability, you can now do explainability for every single log, instead of having to have explainability for the whole sequence of logs you have. But let's take a couple of steps back. So what are we actually doing? We are doing anomaly detection. And there are zillions of definitions of anomaly detection and what it is, but if you boil down to basics, you are identifying rare events that deviate significantly from most of the data. There's nothing more than that. Or if you want it even simpler, which is the one that I like the most, you want to find weird stuff among normal stuff. And that's what we are trying to do here. So when I tell you a log sequence, so software produces a lot of log. Any software produces tons of log. And why do we do log analysis? Well, you want to find errors in software behavior, right? If a software is behaving weirdly, that would show up in the logs. So why not have a look at those logs? And it turns out you can find a lot of cybersecurity threats looking at those logs as well. The problem with it, of course, is that the analyst must manually identify attacks, or they will need to investigate those logs very carefully, manually, and it's very time-consuming. And there are algorithms to do it, but not a lot. And you'll be surprised by how simple the state of the art is. Now, so let's look at a log sequence. So this is a perfectly benign sequence of logs. So a user fills in a username, then they put a password, then they click on the login button, and then the login is successful. That's you logging in on your email or whatever. So that's quite straightforward. That looks pretty normal to me. That one, on the other hand, less so, because they put the username, then the login is successful, then the password is filled in, and then they click the login button. So that one is not good. So that's anomalous. You want your model to detect that one, which is fine. But then this third one, that's where things get interesting, because that's perfectly normal. That's perfectly okay. Just the text is slightly different. And the current state-of-the-art models cannot handle that. So you see here that the username field is populated and the password field is populated. Then the login button is clicked, and then the login is successful. So if you are doing anomaly detection, having that one as your reference, a simple model will say, I don't know what that word is. That's weird. Anomaly. And then your SOC analyst would have to look at that, and they would be upset with you, because they're like, yeah, there's just a small change. No problem at all with that. So can we help them with messages like this? That's what creates what we call instability, or how the log sequence becomes unstable. It's by having differences that are actually not a problem, that are not that are just benign differences, and that's nothing wrong with that. So when you have that situation, that begs this question, I think, and some others too, but we are looking at this one. So how can we identify anomalies in unstable sequential log data? Which is, I think, what I've been motivating up to now. And a couple of things we look at, like explainability. Can we look at every log or alert, for that matter? Can I explain them? Because that would help a SOC analyst to really look at them and have a better understanding. Unstable logs, as I showed you before. How can we deal with that instability? What can we do? And last but not least is the real world versus synthetic data. So you see, how would models that are considered to be state-of-the-art today perform in the real world, in the wild? So give them some real data and see what they do. And the results will be interesting. So let me introduce to you logs. If you ever dealt with logs, you know that logs and analytics were not made for one another. Logs are messy, logs are horrible, and when you want to do analytics, you need to do a lot of pre-work. And this is one thing you need to do. So that's a log on the left-hand side. And this is what we do here. So I keep calling it log keys throughout the presentation. So what you do is that the core of the message is the verification succeeded for a user or a server or an application or whatever. So you just run the verification succeeded for, and then you just want to say all the rest is, individual for that log. But the core of the message is that the verification succeeded for X and Y and Z. So the X, Y, and Z can change, but you want to keep that core of the message right there. And I'm going to call that a raw log message, but most of the time I'm talking about log keys. So cleaning the house a little bit. After you did that, you need to group the logs because you have a ton of logs. Applications generate a lot of logs. And you can do that in different ways. You can have a fixed window where you just group them over a certain period of time. You can have a sliding window where you use, somewhat the same, but they can intercept with one another. And in some types of logs, that's more advantageous than using a fixed window. Or you can do what is also called a session window, where you have an identifier, for example, here 1, and you want to group them in one group of logs, and then you have here identifier 2, for example, and you want to group that as a different type of group. So whatever way you want to do it, what comes out is something like this. So you have 3 different sequences, and then you have, for example, in sequence 1, log A, B, C, D, E. And those are 5 different logs, and that's what we call a sequence of logs, or log keys, I should say. And in sequence 2, you have A, B, 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 and or A, E. So that doesn't matter. But 3 different sequences. And how do you detect an anomaly in those sequences? So you can use a rule. If that happens, it's an anomaly, which is straightforward, very explainable, and that's what most people do. But it's very noisy. So you have your SOC analysts struggling because they end up having a lot of false positives. You can also just do some shallow machine learning, which is better than rules, but you still miss the temporal evolution. So you don't know which log came before. Or in order to get that, you would need to do a lot of playing around with the data. So the order of the logs may be important. Say, for example, in that example I showed you before with the login, if I put a password or the username and click the button, that order matters very much, right? If I click and my login is successful before I put a password, I'm in trouble. Now, deep learning could work, potentially, but where do you start? And that's what we try to do. So this is a first look at it and what we can actually do. There is a lot to do, but this is, I think, a very nice beginning, and people could build out of what we did here. Now, like I said, so many words in those logs and very few numbers. So how do we begin? So say, for example, you have this sentence here, which I wish I had my Manchester accent to read that as Brian Cox, but I do not. So here it says, the moon, Earth's only natural satellite, has been a subject of fascination and wonder for thousands of years. You can do this and just map every word, count. So subject appeared once, thousands appeared once, of appeared twice, and so on and so forth. So you can create information to your model doing that. But as some of you are already thinking, said, well, yeah, there is a lot of words in English, so that's going to be complicated. And the order here also matters a lot. So look at this example. So if I say, raise for everyone, no termination, that's a happy day at the office. But if I say, no raise, termination for everyone, less so. So if the words matter, the order that they appear, that may not be the best. So there are other ways you can do that. So you have your sentence, which in this case is a token of 1, because it's one sentence. If you look at, for example, at words, like I said, it's very intuitive, but you end up with a huge vocabulary. If someone makes a mistake or they misspell a word, that's going to be a different token. That's not what you want. And then you still can have out-of-vocabulary words. People write stuff that is not in your vocabulary. So that's not good. You end up with a huge vocabulary. Well, you can do it with characters, and there are few characters compared to words, which solves the vocabulary size problem. And, so you have a pretty small vocabulary. You won't have any out-of-vocabulary words because you have all the letters, so that's fine. However, you lose all the context of words. You don't know what this T refers to, so that can also be complicated, and you need very long sequences for a particular input. So it may not be the best way either. So this is a good way of doing it. It's kind of a compromise. So you have this smart vocabulary, which is built from characters, say, for example, not from nature, and it can be natural, naturally, and so on and so forth, or, or Asian. So you kind of separate the suffix, and you just keep the core or the kernel of the word. And that really reduces the vocabulary size while still keeping the word that occur frequently, and it's kind of a compromise, which is all right. And it's also robust for novel words, because they will end up having these suffixes and prefixes and so on and so forth. Now, and then you can represent words with vectors. So words with similar meaning, and that's a good thing, they tend to appear or to occur in similar contexts. So, for example, the king waved to the crowd from the balcony, or the queen waved to the subjects from the terrace. Queen and king, they share context in the same way that balcony and terrace. So you can kind of do this and create this context word. So if you're looking at the word royalty, so king, queen, and princess, they share a lot of, well, they have a lot of royalty in them. So that number is pretty high. Or woman, or man, or kid, or whatever, that will have a lot less of it. At the same time, masculinity, so there is a lot for king, much less for queen, woman, and princess. Alternatively, femininity is the same. So you have a lot for queen, woman, and princess, and very little for king. And age, so princesses tend to be much younger than kings and queens, apparently. That's why they have a smaller number right there. And then you can represent them in vectors. And then you can do operations with those. So you start with king, and you subtract men, and you add woman, then you end up where queen is, which makes sense. You kept that royalty, and you can do that for... It's quite funny to do these little games where you subtract and add features and so on and so forth. But that's kind of a simplified way of looking at it. Now, this is the good stuff. And I wouldn't dare to read that, but this is the same sentence as you see here on the left side translated to Dutch using a transformer. And the transformer, we could spend hours talking about transformers, but let's make it simple. You have an encoder that's going to receive the message or the word, and the decoder that is going to, quote-unquote, translate that. So the encoder understands English, and the decoder will write it down in Dutch, right? But you can do a little better than that, because there is this thing called attention. And what do I mean by that? Is that certain words, they need to be referred to. And what do I mean by that is there is this attention mechanism, which is very, very important because, you see, it's important to that sentence that I know, I mean, and we all know here, that they refers to crowd, and rejoiced also refers to large crowd. So you understand that those words have relationships. So if at some point I was talking about, she did this and her dress was great, for example, I could say, well, I know that her refers to she. And this is the attention mechanism that you can do, and that helps us a lot. And that's how our brain tends to work, and we can do that in deep learning models using this attention mechanism. It's not new stuff, but very, very useful just to get the basics in. And then you need fine-tuning. So a lot of those models are pre-trained, so they are given to you, and then what you can do is that we don't have the resources to train those models ourselves. So what ends up, you end up doing fine-tuning and adapting the model to certain words that you want to use, that you want to understand, and pre-training will be way too resource intensive. So we work on the fine-tuning. And BERT models are a great starting point. So BERT stands for Bidirectional Encoder Representations from Transformers. And I showed you transformers before. Use a transformer-based architecture like GPT models do. And it's very heavily based on this attention mechanism. So why is that good? That's good because the embedding of the words can be done with context. What do I mean by that? So I say I go to a bar, and the model knows that that bar is different than I raise the bar, that one bar is better than the other bar, or different, I should say. And they are not the same bar. And that's good because the model is able to know that. So the way we do that, we use this technology or this technique called masked language model, which works in this way. So you have your original sequence here, so log A, B, C, D. What you do is that you mask two of the logs, so you hide them, so the model doesn't know them. And you give them to the model and say, okay, which ones were they? So you expect here to see, well, we know that is log B, and we know that this is log D, right? And then the model outputs something. And in this case, it's correct. It says log B, great. And in the other case, it says log A. So that got it wrong. Now, when you do anomaly detection, the problem is that most of the sequences are just normal. So loads of people try to just implement that stuff for anomaly detection, and it performs very poorly. It doesn't work. So we need to do something slightly different. Well, one thing that you need to add to that system is the embedding layer that I said to you before, because we can't give words to the model, we need to give numbers, and they are randomly generated at the beginning, and as the model keeps back propagating and learning and learning and learning, the embeddings are updated. And we call them initial embeddings. And you do the same thing, you mask your input, and so on and so forth. And the really state-of-the-art current model is called LogBERT. And what LogBERT does, and it looks like the picture gets more and more complicated every slide, but this is it. What it does is this clever thing that you have your embedding layer here, but you have a extra contextual embedding layer that is also trained to try to help you understand which words could be similar. And that's quite a powerful thing. And you can still do that with MLM, with the masking technique that I showed you before. And what this does is that the output then goes to a neural net, and it's going to generate within the logs that you provide, so A, B, or A, C, B, B, or whatever logs they were, within that vocabulary, it's going to generate the probability for all of those logs. Which one is it? So you see here in this case that it says 80% log A, and that's good because we masked here log A. And in this one, well, it should be log B. We know the answer. But it says log C with 90%. So in this case, it was wrong. And you can set an anomaly criteria. So if, for example, the correct token is not in the top X%, you need to look at that sequence. And that helps a lot, right? Or, for example, more of a certain amount of the masked log keys are wrong. That means that the model is not understanding that law, or understanding between quotes. It doesn't really understand. But it's just, okay, this sequence is weird. So we need to look at that differently. Yeah, so that is, happy log, sad log. Now, how can we solve those problems? Well, for explainability, we do this vocabulary-free BERT, which is a improvement of LogBERTs. And one thing that we do is that we do the analysis per element. So it's an element level prediction instead of a sequence level. So as you saw before, BERT will show within the vocabulary that you provided, it would do predictions for all of the logs. So it's almost like it has to understand the entire sentence. And in our case, the prediction would be for a specific log key. So that means that I can, for example, look at this sample, which was correct, and this was correct, and this one is wrong. So I can go and try to understand, okay, give me the information about this part of the log. What did I miss? Why am I wrong here? Is it an anomaly? Is it something that my model doesn't understand correctly? That sounds fine, and we can do that, and we actually do that. But it comes at a price. The price is that this one, the order that you run is much smaller. This is just the order of the sentence you have here, or the aggregation of logs, whereas in this case is all of n, because you have to run for all of the sequence and change for all of the logs. So it's a lot more computationally expensive to run element masking, so you need to mask all of the elements, instead of here, where you just do what you call ratio masking, and you expect to have the whole sequence back to you. So this would be a lot more problematic not problematic, but it will cost you a lot more time to run than the one on the left side for you. So now, if you can afford to do it, if you have a big enough computer, and I'm not talking about gigantic computers here, but it's also probably not going to run on a laptop. When you want to make it vocabulary free, you want the architecture not to be dependent of just of the entry points of the log. So I only know what log A, B, and C are. So you don't want that, because if that's all the model knows, it can generalize. So it will get stuck. So you want to be able to have embedding, or an embedding layer that works without a vocabulary log keys. And that allows you to make connections to different words or to different parts of the vocabulary that you would not otherwise be able to do. And because you do predictions per log, or log key, I should say, you don't need to reconstruct the entire sentence. So you just need to know how close you were for that particular log. And that saves a lot of computation, because the end here is much easier to compute, because you just have to do it for one log. So that makes things faster, instead of having to do probabilities for all of the logs you have. And then, here is only for a couple of logs, so that's fine. But if you have thousands of logs, that is painful. So in terms of architecture requirements, right? we're able to compare the embeddings directly. So, like I said, in a traditional masked language model, you would have the original sequence with all of your logs, and here you would end up having probability for log A, B, C, D, and when you do it vocabulary free, so you play with the contextual embedding, so it can do something outside of the vocabulary, you don't, and you do it per log, you don't need to do all of them here. So, and I'm just keeping the same example, so when you do vocabulary free, you end up having here log B, and that's correct, and this one is log A, that is incorrect. So in a traditional MLM, the model predicts missing words by reconstructing the whole sentence, and it said, okay, this is the word that is missing, so let me look at my entire sentence. Oh, okay, is this the right word? Yes or no? And in vocabulary free, that's not what happens. You're just gonna predict a particular word that is missing without the constraint of that fixed vocabulary, and that is much, much better. Now, let's look a little bit to our data, and happy because that paper got accepted last week, so I'm happy to say that it's accepted there to the ACM Symposium on Applying Computing for next year. So what we do here is you have logs coming in, and you have loads of detection systems, and they are generating loads of alerts. So what I showed you before is for logs, and the real example that we are looking here is for alerts. So what do I mean by alerts? It's a detection system, and you can think of network detection, servers, endpoints, applications, and these systems spit out alerts, right? So everything generates an alert. And if you understand the Security Operations Center problem, they have to deal with a lot of false positives. So most of those alerts are just noise. I always say that it's like their job is like Tinder only with ugly people, because they just say no, 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 no the whole day, and that's frustrating. So what we did is we said, okay, let's put a analytics or an integration layer in the middle to separate the alerts from the analysts. And what we do here, and you can read it in the paper, I'm happy to share with you, is we create mostly machine learning models or very clever rules if the situation merits that, but mostly using advanced analytics. And those models will reduce the number of false positives, and then the analyst will have a lot more time to look at really interesting alerts. Yeah? Now, looking at results. So how did we do? So looking at the evaluation of the data, so we are using 3 very frequently used data sets, or log data sets, so the Hadoop one, the BGL, or the Blue Gene, and the Thunderbird. And we are using the ING alert set. So you can see here that you have millions of logs and hundreds of thousands of alerts, and the anomaly is always pretty low. 2%, 1%, 4%, and so on. So most of this stuff is normal, as you would expect. But now we make things a little spicier, a little more complicated, because most of the time, what you see is that when you separate it in train and in test, is that most of the stuff in test, you could have a very simple system that when you're testing the model, and it doesn't have to be machine learning, a simple heuristic will do, that, oh, have I seen you before in train? No? Oh, you're an anomaly. Just that. And that works really well. But I would argue that that works really well because the data is quote-unquote very simple and presented and separated in such a way that allows for that. So we want to see, okay, what if we make it a bit more difficult and we have a lot of stuff in the test set that is normal, but is not an anomaly? How will those models work? So, for example, instead of saying login OK, you say login accepted. That's normal, but it wasn't in the training set. So will the model understand that it's all right? Or will the model just say, yeah, I never heard the word accepted, SOC analyst, do your thing. No, that's not what you want. Now, so what we did is that look at the original split of all the papers that we found out. So the main LogBERT paper, for example. The normal sequences, so the blue line here, it contains less than 5% of the unseen logs, whereas the anomaly sequence contains over 80% of the unseen. So it's quite straightforward that if you say, okay, I've never heard of you before, that's an anomaly. And you start already being right 83, 84% of the time. Don't have to do anything. Never heard of you? Anomaly. And what we do is that we increase that complexity. So we make a lot of normal sequences by reshuffling between train and test that are actually different. So the model has never heard of it in training, but they are not anomalous necessarily, or they are still benign. So let's have a look at that. And this in green, that's what everybody does. That's what everybody uses. Is this heuristic that I told you? So here on the y-axis is a coefficient score that goes between minus 100 and 100, typically between 0 and 100, as it should go. 0 means complete noise. 100 means you got everything right. And most people use, and on the x-axis, sorry, let me just explain. So that's the percentage of normal sequences containing at least one unseen element. So think of this easy data, and think of this difficult data. Data with a lot of normal stuff, that is different, but it's still normal. So you see that in this particular run, which is the run that they show in the paper, the unseen, or the heuristic that just says, never heard of you, anomaly, works really well. So they make the point that this is enough for what they are doing. And the reason is what I showed you before, is that because most of the unseen stuff, it's in the test set, was not in train, so you would just say anomaly, and you're good to go. But as you make things more complicated, you see that both models, both LogBERT and the unseen heuristic, decrease the performance significantly, and VoBERT maintains a much more constant performance. Well, you can say it's not as good as here, which is a fair point, but this is not, there is no hyperparameter tuning here, which I want to make very clear as well. So there is a lot of potential to make this model overall better, and most importantly, those scenarios tend to be very unrealistic. You would not have something that behaves like this, or not having normal sequences that contain an unseen element. So most of your test sets will be much more complicated than this. And this is the test in the real data, where VoBERT and LogBERT perform more or less the same, and I come back to that in a second, but look at the heuristic. So this is, when I see that, that's why I told you this story about me driving my car. This is the heuristic that people say it's fine. So as soon as I start to have more complicated or more normal sequences containing unseen elements, the state-of-the-art model, or the model that everybody uses, gives you a Matthews coefficient which is even below 0. And that actually means that it's almost becoming good, as in, if I tell you right, it's actually left. So it's worse than random. It's almost getting precisely the wrong thing all the time, which is horrible and not what you necessarily want. And this really opened my eyes, and we can't have only papers looking at that type of data set where, it's kind of easy, or looking at some of those models where the test data is just kind of artificial. So we need to look at the real stuff. So let me wrap up, and we can have, I think, maybe one question if time allows, but we used a transformer model to leverage this sequential data, as I told you. The solution remains stable for log data environments, which is good to see. You can do explainability if you want, and if you can afford the resourcing, that will be beneficial for you. And LogBERT performance, and especially the heuristic performance for real-life data, that's not what you want to see. So we need to remember that we need to keep doing research and bridge the gap between academia and industry as well. And that's the link for the master thesis if you want to have a look. And I'm not sure I have time for questions, but I'll be here around and we can have a chat. Thank you.